name is Katarina Hafner-Vuk and I work in the Institute of Metrology of Bosnia and Herzegovina as one of the main partners in this biomed project. Within the scope of the training sessions, I will tell you something today. In today's presentation, I will tell you something about the elemental analysis in solid biofuels and resulting ash. So the scope of this presentation covers the introduction to the topic, some guidelines on sample preparation, and the overview of existing analytical techniques and methods. First, we need to say something about wood pellets and one of the representatives of solid biofuels. So wood pellets are usually made of compressed sawdust or whatever waste from the wood industry. In that sense, it's a really perfect type of fuel since it's very filled with energy, it's in powder form, it's easy for it to burn, and usually no additional glues are required since the lignin is already present there in a wood material. The problem occurs with the dust collection that can contain additional, typically some inorganic content apart from wooden content. You can see here in this slide what is a typical source or general properties of wood pellets, and you can see that the main parameters to be measured would be calorific value, content of ash and moisture, bulk density as well, but of course in order to assess the real quality of whatever fuel, including solid biofuels, some additional testing needs to be done in order to assess inorganic and organic impurities. Today's presentation is really dedicated to the analysis of inorganic impurities that can have some effect on the environment and also can affect calorific value. Also, ash is very important. That comes as a result from burning of solid biofuels. In this particular case, it's wood pellets. So both the main constituents of wood would be carbon, hydrogen, nitrogen, phosphorus, sulfur, and other elements, usually non-metallic elements that are forming the majority of the material that is of wood. But of course, some other elements are also present. Since most of these inorganic elements are lost during combustion in forms of some gases, mineral content of pellets are being actually concentrated in ash, and that is also one of the ways to assess very low concentrations of certain elements. Talking about the elements in pellet and also then being concentrated in ash, they can usually be divided into two groups, so major and minor elements or trace elements. Major elements would be those elements that are normally present in wood material, in plant material. So as you can see, calcium, potassium, magnesium, phosphorus, sulfurous, iron, sodium, and some others, and silicon maybe, and also for the trace elements could be some elements that are also important for the metabolism of the plant, such as manganese, bore, copper, zinc, but also some heavy metals can be present there. The presence of these major and minor elements can also tell you something about the wood material that was used. So major elements can also tell you something about the type of the wood used, how it was processed, does it contain more of the what part of wooden material is present in a pellet. That can also affect its quality in terms of calorific value, but the presence of some trace elements such as heavy metals can also tell you about the potential pollution on that soil where the wood was growing, the pollution of air, but in majority of cases the presence of these trace elements usually come from the dust that is collected together with the sawdust, together with the wooden material that can also contain some mineral content. This is important because these particles, when pellet is burning, this mineral content will not completely remain in ash, but can also be transferred in air, in small particles. And also, after ash is being formed, some additional precautions need to be taken in order to treat that ash in a proper manner, not to transfer further the concentrated pollution with both major and trace elements further in soil and surface waters and so on. So that's why it's very important to assess the elemental composition that is also telling something about the quality of biofuels. Of course, in order to assess elemental content, you also need to have very representative samples. Talking about this type of bulk sample, such as wood pellet, it is usually not so homogeneous on a small scale, and for these type of techniques, you usually need maybe several grams of material for making subsamples, for making analysis. That's why it's very, very important to do everything that is possible to take representative sample from the field, and then of course to take the subsamples out of it that can be tested for, of course, reproducibility, in order to assess whether the sample was sufficiently homogeneous. If that is impossible, then of course you need to analyze many more subsamples in order to assess the real quality of biofuels, in this case wood pellet. And of course the sampling part is also important from the part of metrology. It is also a part of uncertainty of measurements. So not only that it's important to take the representative sample to make this source of the uncertainty as small as possible, but what is even more important is to make it quantifiable, so that you really know that you are capable of assessing the measurement uncertainty coming from sampling. And one part of this project is really dedicated to sampling. When it comes to sample preparation, it is very, very important, and typically the sample preparation will depend on the analytical technique that will be further applied for the chemical analysis. If some optical methods or spectrometric methods of analysis are being applied later on, that usually means that you need your sample in liquid form, and that also means that since the focus is on elemental analysis, these elements need to be in some kind of analytical form, usually in the form of cations or anions, and they need to be homogeneously distributed in the liquid that is formed. It can be also done with some organic extraction, but majority of methods for sample preparation are actually recommending some sort of acid mixture with maybe some additional oxidants in order to successfully digest the whole sample and transfer all the elements or the analytes into homogeneous analytical forms. What you can see here in the photos is one example of microwave digestion unit, where you have Teflon vessels in which you weigh the sample directly and then add directly pure acids or some other reagents, where by means of microwaves this digested is being heated and digestion is being promoted with that heat and additional pressure. So it's very quick and it's very quantitative in terms of minimum possibility of cross-contamination between samples. When it comes to some non-destructive methods, such as, for example, X-ray techniques, it is also possible to prepare the sample in different way without destroying it. So those methods are usually non-destructive methods, and that means that both pellets or ash made from burning of pellets can be also compressed into some kind of pastel, into some kind of tablets that can be used more than once in order to assess the elemental content. This is done by means of X-rays. Usually there are some other techniques, but you will see in some of the next slides what is the principle of this X-ray technique.